which are high energy probes, and then electrons. Most common probe, apart from light, is actually electrons. So we will deal a bit about electrons in the next couple of minutes. Now, when you take an atom, you have atoms with shells of electrons, okay? And electrons in atoms can be split into two parts. One is the valence electron, which is the outermost electron, and you have the core electrons. Now, when you take an X-ray photon, if you remember the spectrum, the electromagnetic spectrum, you know that X-rays are much larger energy than UV rays. Okay, so now if you take an X-ray and then send it to an atom, what it does is it's actually so high energy that it can go and knock out the innermost electrons or the core electrons. And the outgoing electron, which is called a photoelectron, because it's generated by a photon, it has a kinetic energy depending on what was the energy lost in knocking it out and the incoming energy of the incoming photon. When you send a UV photon in, it is not as high energy as X-ray, so it knocks out valence electrons. Both these events help us get some information about what is the atom. Now, that concept behind how we derive the information that we need is called photoelectric effect. Now, the equation is very simple. You have a photon that has energy, and that's the energy that we are supplying. And you spend the amount of energy knocking out the electron. That's the binding energy with which the electron is held, and that's the binding energy. So the electron comes out with the kinetic energy, and the kinetic energy is equal to the initial energy of the photon minus the binding energy. It's that simple. Now, if you take an atom, okay, let's say you take a carbon atom that's bound to a fluorine. You take a carbon atom, let's say it's bound to hydrogen. We compare these two situations. Now, fluorine is has higher electronegativity than carbon. What does that mean? It means that a carbon-fluorine bond, the electron density of the bond will be closer to fluorine. And in the case of hydrogen-carbon bond, hydrogen is electropositive when compared to carbon. So the electron density of this bond will be closer to carbon. Now, depending on whether the carbon has lost or gained electron density, the energy required to knock out the 1s electron will be different, and that's what it's shown here. For example, the energy required to knock out the 1s electron of carbon, in the case of carbon-hydrogen bond, is 285. In the case of CF bond, it's 291. It has gone up. The reason is the electron density is being lost from the carbon atom, so this electron is held even more tightly because it has lost electron from valence bond. So now, based on the measurement of the binding energy, which is actually done by using this equation, by measuring kinetic energy, you know the incoming photon, so you can calculate the binding energy. So if you take a sample and then send a bunch of X-rays, if you get a lot of 285 eV photoelectrons out, that means your sample has CH bonds. Okay. On the other hand, if you get a lot of 291 eV electrons out, that means you have CF bond. And the same applies here. I'm talking about one specific chemical bond. It applies to elemental information as well. Now, hydrogen, the 1s of hydrogen has a binding energy of 15. And carbon has binding energy somewhere around 285. Oxygen has 532. Fluorine has 685. So if you get a peak at around 285, that means the sample has carbon. If you get a peak at 685, it has fluorine. So this information gives elemental composition, and this gives, if you do an even more detailed analysis of the electrons that are coming out, you get even detailed oxidation state information. Okay, this whole process is called electron spectroscopy, where you are using the property of electron that has been knocked out by a photon, which is called a photoelectron. That's why this whole spectroscopy is called photoelectron spectroscopy. Okay, we can, based on the kinetic energy of photoelectron that is coming out, we can get chemical information. Okay, that's the conclusion from this slide. Now this takes us to the next question, which is how do we, in the previous lecture, I told you how to analyze, how to select wavelength, that's by dispersion. Now how do you measure electrons of different wavelengths? How do you distinguish one electron from the other which vary in wavelength? Kinetic energy. Okay, and that is what is the next section of this lecture about. How do we build an electron analyzer? Okay, now we use electric field. Electron has a negative charge. As I mentioned before, charges in electric field experience a force. Now, if you take two plates and you connect it, one to the negative of a battery and the other to the positive, so you're applying a voltage. It's that simple. And let's say you send two electrons. One is a high energy electron, low energy. Here, kinetic energy translates to wavelength. Okay, higher the kinetic energy, lower the wavelength. Or the higher the kinetic energy means higher velocity. Okay, for electron that's how it translates to. But in light, the velocity remains constant. But in case of electrons, higher kinetic energy means higher velocity. Now, along the x direction, the displacement is directly proportional to the velocity. V stands for velocity. And along the y direction, how the electron gets displaced along the y, that is inversely proportional to the velocity. So now you send two batches of electrons, one high energy, one low energy, and this will be the trajectory. Okay, the higher energy one will travel further, and the lower energy will go much smaller distance. Now, if you see, this is actually dispersion of electrons based on the kinetic energy, and if you have a detector here, you will detect the low kinetic energy electron. If you have a detector here, then you will detect the high kinetic energy electrons. Okay, so now I'll give example of a setup, actual setup, how electron spectroscopy is done. You have a source of X-ray. You can also have a source of UV ray, which knocks the photoelectrons out, and the electrons travel up, and there is an analyzer. Now, the one of here is an example of how to build an analyzer. For example, if you see, this is a hemispherical analyzer. Okay, you have an outer sheet and an inner sheet that are in the shape of a hemisphere, and they are just like what we did here. We apply voltage, opposite voltage. Now, just like what happened here, there is dispersion of electrons based on the kinetic energy of the electron, and when the electron reaches here, and it gets dispersed, and only the electron that has the energy that we are intending to detect, that comes out, and all the remaining ones, they hit the walls. Okay, this is one way of analyzing photoelectrons based on their kinetic energy. And what are the techniques that use this principle? It's transmission electron microscopy, scanning electron microscopy, and X-ray photoelectron spectroscopy. You will be studying all these techniques in detail, one lecture at a time in the future. Okay? Now, the other property that I want to talk about is, now we spoke about light, now we spoke about electrons, now we combine these two. Let's put electron and light together. Okay? The other property is piezoelectricity. I'll come to surface plasmon resonance first. Now let's define what is a plasmon. Okay, you take a volume of material that is neutral, and let's say just imagine that you pull the negative charges at this end. All the negative charges, you pull them just a bit by a distance delta. Now, because you separate the negative charges, that creates a bunch of positive charges. You pull it and let it go. So, and then they vibrate for some time. Okay, they neutralize and then they overshoot and then they come back. And this vibration, collective vibration of electrons, is called a plasmon. Okay, plasmon is an imaginary particle because there are no positive charges. Actually, there are no positive particles. It's just the absence of electron. That's what you're imagining as a particle. Okay, that's why it's called a plasmon. Even photon, the word photon that is used for describing light, that's also an imaginary particle. There is nothing called actually a photon. Okay, now if you take a surface of a metal, we all know that it has a lot of free electrons that's in the conduction band, and light consists of electromagnetic wave, especially the electric field is important. Now, if the wavelength, the frequency of this electric field matches the frequency of electrons that are in the metal. Electron, even though it's a particle, it also has a wave nature. Okay, all the subatomic particles, all the quantum particles, they have both wave and particle nature. Okay, now we are going to consider the wave nature of electron. Now, the electric field of the light wave couples with the wave of electron, and if the frequencies match, then they undergo excitation. Okay, and depending on the electronic property, which depends on the material, the metal that we are choosing, depending on the surface and the surrounding, what surrounds, if it is air, is it water, is it something else, and also the angle at which the light is incident. The degree at which the light couples with the metal is dependent on all these factors. Okay, and when they both match exactly, and there is maximum transfer of energy from light to the collective oscillation of electrons, that's called the surface plasmon resonance, and the particles that are the oscillation, wherein the electron, the bunch of electrons coupled with the light, that entity is called the polariton. Okay, I'll just explain this again. So now you have a light wave that is incident on the metal, and this causes the collective oscillation of electrons, and that creates an electric field. Okay, and the entity that is combined together, light and the electron population together, population of electrons and the light together, that is called the polariton. And the process where there is maximum transfer of coupling of electric field of light and the electron, that's condition is called resonance. And since the collective oscillation of electrons is involved, which is called a plasmon, that's why this whole process is called plasmon resonance. And this happens a lot on the metal surface. That's why it's called surface plasmon resonance. Okay, so now how do we use this process to get some useful information? Now, let's say you take a surface of metal, okay, and there is incident light and it's getting reflected. Okay, depending on the angle, now you have the resonance, surface plasmon resonance happening, and the surface plasmon resonance creates electric fields that oscillate on the surface. Now, the resonance condition depends, as I said in the previous slide, it depends on a lot of factors, one being the metal itself, the other is the medium, the surrounding medium. So if there is a change in the surrounding medium, then the resonance condition changes, it's altered. Okay, so now let's take a setup, actual setup, how we use the surface plasmon resonance to get some useful information. Now, we set up a polarized light wave that is incident at an angle, and let's say we set it up such that there is resonance happening, surface plasmon resonance happening, and that depends on a lot of conditions, as I spoke before, and mainly the surrounding medium. Okay, so now you have the surrounding medium and also the angle of incidence. Now you have a channel that is supplying some fluid on the surface of the metal. Okay, now let's say you have some antibodies. If you don't understand, don't worry. Let's say there is some reaction happening on the surface where there is some deposition happening. Okay, now depending on how much deposition is happening, at what rate it is happening, the properties of the surrounding medium changes. And surrounding medium changes, that means the condition for resonance is altered. Now, there are two things that can happen. One is you have intensity, the angle, the optimum angle at which resonance happens shifts. Okay, so now let's say you have situation 1 where you started with, and once you send the sample, because of the change in the environment, you have the resonance angle at which resonance happens changes. And depending on how much the angle has shifted, the resonance optimal angle has changed, you can tell how much of this process is happening. Okay, so this is a very clever way of detecting what is happening at the surface. Okay, now I will talk a bit about piezoelectricity. Piezoelectricity is a property where you apply a potential across a material and it undergoes mechanical transformation. Okay, so now mechanical stress on a material generates electric field, that is the piezoelectric property, and the opposite, where you apply potential and the object changes shape. Okay, that is called reverse piezoelectricity. I'll go deep into detail how this happens. Now, if you take any material, there are two possibilities. The crystalline materials, they have groups of atoms that are aligned exactly in the same fashion. Okay, they're crystalline for that reason. Now, you can have an entire material, single crystals, for example. They have all the atoms pointed in the same direction, atoms or molecules. On the other hand, if you take a polycrystal, you have domains where you have a limited volume of material that has atoms or molecules in one direction and the other pointing in randomly other direction. So you have the entire material divided up into volumes with different orientation of molecules. Now this is called polarized, and this is called polycrystal because the polarization is in the random directions for each of these domains. Now, if you take a material that is randomly oriented domains, and then you apply external voltage. As I mentioned before, if you apply voltage, that produces electric field and that aligns the dipole moments. And if you do this at a very specific temperature, then once upon removal of the voltage, the rearranged dipole moments, they tend to stay there. They don't go back to the random. Okay, and this process is called poling, where you apply a voltage and then you make it polarized. That entire process is called poling. Here is an example, specific example of why poling happens. Okay, now you take a material which is randomly oriented. For example, here I'm talking about lead, titanate, zirconate. So you have this is the unit cell of this crystal. If you see at the center of this is the titanium 4 plus or zirconium 4 plus cation, and it is surrounded symmetrically by oxygen 2 minus. Okay. Now, when you do poling, what happens is the molecule gets stretched, the entire unit cell gets stretched, and if you see the position of the cation, the titanium or zirconium, it gets moved towards this. This creates a dipole moment. It's no longer surrounded equally by oxygen. Okay, so that means this region of the molecule has a slight positive charge because the cation has moved up, and this region has a partial negative charge, and that's what I'm showing here. Here there's a positive and there's a negative. Okay. Now the molecule, as you see, it gets stretched and it also gets a polarity. There are several other molecules that can do similar thing. Now I want you to imagine something. What if you, instead of applying electric field, if you press this physically, then what will happen is this will go into this conformation. If you physically press it manually, then it will also behave the same way. Okay, so that's what is the basis of piezoelectric effect. Now you take a material that has undergone this poling process, okay, and let's say this is the potential, poling potential polarity, positive and negative. Now when you apply physical stress, mechanical stress, because it undergoes this transformation from this to this, and if you invert this, okay, now this cation will go to the reverse, so the polarity will reverse. Okay, that is what is the basis of this. Now when you physically strain this pole object, you have external voltage developing. So when you press, you can get electric voltage out of it. And the other process is you can apply voltage vertically, you can also apply voltage horizontally. And it depends on what kind of transformation you are doing to this molecule and how it's oriented. Okay. Now the opposite effect of this is, now in the previous slide I told you where you apply mechanical stress and that creates a potential. Okay. What about if you apply potential and it creates a mechanical motion, okay, transformation. That is what is happening here. You have a material that has been subjected to pulling, and it has a pulling voltage. Now, instead of measuring voltage, let's say you're connecting it to a battery or applying voltage, and that, depending on the polarity, positive, negative, positive, or positive, negative, the pole material undergoes either transformation vertically or horizontally. Okay, and depending on that, you can achieve vibration. Okay, I want you all to guess something. What will happen if you apply? So now here I'm talking about applying negative and positive and positive and negative. What if you apply a AC voltage? What do you think will happen? What is AC voltage? What is alternating current? Okay, now you have positive and negative. In a battery, you connect a positive and negative, it remains positive and negative forever. But in alternating current, it changes sign every now and then. So alternating current, the reason why you call it alternating is because positive becomes negative, negative becomes positive, and that keeps flipping all the time. Okay. So now let's guess. Okay, now I've told you what is alternating current. Let's say you keep flipping this all the time. What will happen to this material? It is going to exhibit vibration, right? It's going to contract horizontally and then contract vertically, expand back and then go back. So it's going to do this repeatedly, and that's exactly the property that we are interested in. Okay. Now the reverse piezoelectric effect can be used for vibrating materials at a very, very controlled fashion. Okay, because you control the amount of current that you give, amount of voltage that you give, you control the vibration. Here are the techniques that you will be learning in this course that use piezoelectric effect as the basis of measurement. One is quartz crystal microbalance, the other is atomic force microscopy. I'll just start with quartz crystal microbalance. Here what we have is a piezoelectric material, which is a quartz crystal, okay, and it is sandwiched between two electrodes. This is the upper side of the electrode and this is the lower side. Usually this electrode is gold. Now, as I told before, if you apply an alternating current to this entire setup, now you have here the polarity is, this is positive and this is negative. Here if you apply an alternating current, it is going to vibrate back and forth. Okay, and this vibration has a frequency. Now what we can do is this electrode, if we do some surface reactions on this end of the electrode, and depending on the AC current, it is going to vibrate, and how much of reaction happens if there is something getting deposited or if something is getting lost from the surface. You have an initial frequency, and depending on the change in mass of this upper layer, you have change in frequency. Okay, because the mass of the vibrating entity itself is changing, and that leads to change in frequency. And depending on the amount of change in frequency, you can detect the change in mass. So this has sensitivity of up to nanograms per centimeter square, and that's one of the most sensitive weighing techniques that we have today. Okay, now I'll show a cross section of how the measurement is done. You have a quartz crystal, and you have a working electrode, and you have a counter electrode below, and here's the cross section. Now you have a flow of liquid, and the flow is going out. If you subject this to some reactions where this flow is incoming with some chemicals that deposit on the surface, then you can register that as a change in frequency, in vibration, and that you can convert it into mass information. Okay, the next thing that we're going to deal with is a vibrating beam. Okay, now if you take a beam, it's called a cantilever, okay, or a beam. You put a piezoelectric material here, and you apply AC voltage. Now, depending on whether it's contracting or expanding, the beam is going to move up and down. Okay, and when you apply AC voltage, it's going to vibrate at a frequency. The distance the end travels, the maximum distance it travels is called amplitude. Now, phase is you apply a voltage here, AC voltage, and this is exhibiting a vibration. Now this also has a phase. Okay, I can draw that. Now let's say the AC current that you apply, it has, and the phase is the state of vibration, okay? Now with time. Now the beam, let's say its vibration is this, okay, exactly following the AC voltage that you applied, then you can tell that it's in phase. But then if the vibrating beam, let's say it is undergoing a bit of delay, then the distance between this and this, that's the phase difference, okay, the angle between this, that's the phase difference. And that also gives valuable information about what kind of processes are happening. Okay, here is the actual setup, atomic force microscopy. What it consists of is a beam which has a piezoelectric material at one end that makes the cantilever vibrate up and down. And a laser beam is reflected off from the back of the beam cantilever, and it falls on a photodetector. Now the photodetector is called a position sensitive photodetector, and it's a quadrant photodiode. The way it works is you have 4 photodetectors, and you start off the instrument by making the laser fall exactly at the center, and depending on whether the cantilever is moving up or down or sidewards, the beam also moves up or down or sideways. And depending on the signal transduction that happens here, you can predict how much the cantilever has moved and in which direction it is moving. And that is the basis in which you can use a vibrating cantilever to measure interactions between a surface and an AFM tip. Okay, this is the actual setup, how it looks. You have a cantilever, as I told before. You have an incoming signal, and the cantilever is vibrating, and that vibration is detected as an AC signal again. Okay, so now by matching these two signals, this is the incoming signal, this is the outgoing signal, you should be able to guess what the surface is. Now, based on amplitude, you can tell the height. Based on phase, you can tell a lot of other properties such as chemical properties. You will hear a lot more about this in the AFM lecture that will follow. Okay, so now this is a summary of the second part. We dealt with photoelectric effect, and then we saw how electrons travel in the electric field, how this can be used for analyzing electrons. And then we have surface plasmon resonance, where we saw how light couples with population of electrons on metal surfaces, how that can be used to our advantage when it comes to studying surface processes. And we also dealt with piezoelectric effect. We saw 2 techniques. One is quartz crystal microbalance, which is a surface sensitive technique where we detect the change in frequency and relate that to change in mass of the electrode. And you have atomic force microscopy, where we have a vibrating beam, and that is used to image surfaces morphology. Okay, this is kind of all the basics that you need to understand, all the techniques that you're going to deal with for the rest of the course.